Time for a pop quiz.
Zeta surprised! The reaction is like finding a missing variable in an equation. Unexpected, but exciting. What's got you all Zeta wide-eyed? Spill the beans.
Huh, nicely integrated.
Hello everyone, welcome on in. My name is Penn Center. We're here for our first Summer of Machine Learning session, which I'm a little excited and nervous about. Hi Martin, yes, you got your QED point, don't worry. Enigma bot's just broken right now, so we have to do it. We have to do things manually again for the interim until I fix that. Hi Oakley, if process is directly equal to branching, then cry. Yes. Oh no, your summer research stuff is hard? Is that why I haven't heard from you? Ads are longer than my arithmetic. True, yeah. If you run a 3-minute ad at the very beginning, then pre-rolls are off. Pre-rolls are now off for an hour. So people that want to come in and join us don't have to face that like annoying 30-second ad when they join. So without further ado, since I'm on a little bit of a time crunch today, I do have a hard cutoff time in about 2 hours. Let's just kind of go through a general overview of where everything's going to be. This is going to be like super informal. I have like literally nothing planned. My thought process is basically to utilize my Friday mornings, which tend to be fairly free for me, to read through some materials, right? And that way we can chat live together if we want. We can do a little bit of programming. if we need to do some programming. The textbook that I'm using uses R, which is a free downloadable software program. So that's available to us. I know there's been some interest, I think, with Tyrion for work in Python. So if any of you make Python scripts and want to add them to the resources, that's cool. I've posted a forum so that if we need to add some resources, we can do that in the forum. You can just add it to the resources post, or you can make your own post. Doesn't really matter to me. If there's any kind of general chit chat, we have a space to do that here. And then for announcements, I'll throw them in. So there's just a couple channels here. What are my perms here? Just out of curiosity. I think everyone has access. No, you have to have the online classes tag. So as long as you have the online classes tag, you should be able to view everything. And if you're wondering how to get the online classes tag, I think you just have to come up here to rules and roles. That's a math stream. Oh, maybe it's up here. You should be able to do it in the channels and roles at the very top. Extracurricular, maybe a bit of both. Yeah, so it's just right here at the top. If you want the online classes tag, so you have access to the channels, just click please give me the role, and it should automatically assign that to you, and then you'll have access to the machine learning section there. So I'm just going to be kind of roughly reading through Reese's machine learning with R, as well as James's statistical learning during these sessions, just to try to get a better idea of what I kind of have a general sense of what machine learning is, but I'd like to learn a little bit more about the underlying mathematics. That's my goal. So we offer 2 machine learning courses and 1 mathematics for machine learning course at my institution. And this is probably one of the few courses where I am not super familiar with the content, so I want to just kind of go through it, try to understand that content a little bit more, and maybe do maybe do some script writing or something like that. We do things manually in a machine learning stream. Yeah, I want to do some stuff. I want to write some scripts. I want to machine learn on these data sets. So today's goal is just to maybe read through the first chapter or 2, depending on our time. And then we'll probably I want to kind of start into classification next week. Yeah, there's Reese. Reese has had a very good walk this morning. He's just chilling. All right, let me get geared up here. I don't care about the preface. Does anyone read acknowledgements? I don't know. Holy moly, there's a lot of stuff in here. Okay, here we go. This is an introduction. Where's our actual chapter 1? Here it is. Introduction to Machine Learning. Yes. Hi, caller. How you doing? Hello, Glorp friends. Where's the Glorp emote? Where is it? Finally, no DayZ, no Factorio, no financial math, no math education, no syllabus making, no accounting, just math. We'll see. I make no promises. Okay, I don't care what the chapter covers. We'll figure that out along the way. I assume there's nothing super exciting here in the first little bit, so we interact with machine learning on a daily basis. Yes. Very clearly. Marketing uses it a lot. Faces in the photos you upload to social media platforms are automatically identified and tagged. Wow, that raises so many ethical concerns to me, but I suppose if you have a social media site, you probably have already signed your life away, right? Because technically your facial data is unique to you, so it should be a personal identifying piece of information and should be protected under a lot of the rules and regulations, right? A lot of the laws. Unless you sign away your right, which I suspect you probably do on Instagram, which I guess is Facebook now, which is, I guess, all under the Meta flag, isn't it? Is that how it works? Your car's GPS predicts which routes will be busiest at certain times of day. I've certainly seen that on Google Maps. Or it can tell you, like, where a crash is. Like, how does it know there's a crash there? Does someone just report a crash? Your email client progressively learns which emails you want and which ones you consider spam. Yeah, I find that funny. To make your inbox less cluttered. And your home personal assistant. Who the fuck has a home personal assistant? Who has that? Is that like your Hey Siri or like your Hey Amazon or like Hey Google? Home personal assistant? Is that really a personal assistant? That's just a robot collecting data from you. That's just a data mining robot. That's all that is. It's like Alexa. Okay, Siri and Alexa. Okay, got it. Talking about machine learning, though, not AI, so there should be no ethical concerns. The collection of that data has ethical ramifications. So if it's already inside of a machine learning algorithm, it's probably okay, right? You probably. But there were lawsuits, I think, against. I present on this in my capstone class. There was a lawsuit against Flickr. I think there was a lawsuit against Flickr because Flickr took all of the photos that were inside the database and sent it off. And somebody sued because that's protected data. So that's Avianca, that's Suno, IBM. Oh, do I not have Flickr here? Oh, maybe it is IBM. I feel like Flickr's Yahoo, though. But yeah, there's pretty big ethical concerns when it comes to, like, scraping that data without actually notifying people that the data's getting scraped. Yeah, and do you agree to actually having your voice used when you use a home personal assistant? Is there an underlying agreement there that you're agreeing that your voice and that data is getting collected? I don't know. I've never gotten a home personal assistant because it scares me too much. I'm like, I don't need that data being out there. Oh, some of that robotic surgery stuff's pretty fucking cool, though. Another automated scanning for other Earth-like planets. Yeah, good luck. Okay, it's cool. But here's something I want you to understand right away. Machine learning isn't solely the domain of large tech companies or computer scientists. I suppose that's true. I suppose anyone with a reasonable background in statistics, calculus, and linear algebra can probably do this work. Here it is. Anyone with basic programming skills. Yeah, programming skills we need.
Big applications are like complex functions,
In their
each
work.
with its
If
own
you're a scientist,
purpose.
machine learning gives
Dive
extraordinary
in,
insight into the
analyze,
phenomena
and
you're studying.
discover
If you're
their
a
hidden
journalist.
beauty. What's caught your Zeta attention?
What's this? Delineate your story? If you're a business person, machine learning can help you target the right customers. Yeah, so in our marketing classes, we're probably trying to hit KPIs. We don't really have like a journalist section. I'm thinking about getting a journalist section for our data analytics stuff. We also don't have like bioinformatics yet, which would be super fun to get.
Remember, an assistant's performance is all about efficiency. Can it compute fractions or solve for x? Results matter, not favorites.
What?
Zeta, hello. Prepare for some mathematical madness. What's on your mind?
It says, while you won't be building intelligent cars or talking robots after reading this book. That's the whole point of reading this book, is to develop talking car robots. That's all I want to do, is build talking car robots. Okay, fine. Going to teach the theory and the practice of machine learning at a level anyone with a basic knowledge of R. Cool. That's all I really have is a basic knowledge of R, and anything that we don't know we'll just throw in the chat GPT. Everett, because it's actually quite good at coding now, which is surprising. Ever since high school, I've been terrible at math, so ever since high school, I've been terrible at mathematics, so I don't expect you to be great at it either. Huh. Is this the right book for us, chat? Is this the right book for us? Ever since high school, I've actually been good at math. Welcome in, Everton's Best. I don't know, Addy. I don't know. 0 out of 10. I don't know. The only reason I picked this particular book is it's the one that we typically use for our machine learning courses, because our students might be terrible at mathematics as well. But I'm hoping the statistical one will go into a bit more depth on how we do some of these algorithms, at least from the math side. Okay, there are no hard concepts in machine learning. Okay, cool. All of the processes will be explained graphically and intuitively. Great, I would hope that a textbook would do that. Okay. In this chapter, we're going to define what I actually mean by machine learning. So we're going to get a definition of machine learning. I hope it's in a box. Okay, imagine you work as a researcher in a hospital. What if, when a new patient is checked in, you could calculate the risk of them dying? That would be pretty cool, actually. This would allow the clinicians to treat high-risk patients more aggressively. True. And potentially result in more lives being saved. Yeah, I can get behind that. But where would you start? What data would you use? How would you get this information from the data? There it is. There's our key in. We want to use machine learning. Machine learning, sometimes referred to as statistical learning. Hey, wouldn't you know?
A zeta funny. Treat aggressively sounds like a chaotic equation. Unexpected but intriguing. Just remember, in math and life, clarity rules. What context are we diving into here?
Treat aggressively. I know. It doesn't sound right, does it? I'm going to treat you aggressively. All of my hand motions are going to be strong. Please don't flip that. Okay, so they're saying that machine learning is a subfield of artificial intelligence whereby algorithms learn patterns in data to perform specific tasks. Sure. Okay, so machine learning is a subcategory of AI. AI is the umbrella. Although algorithms may sound complicated, they aren't. I mean, well, I would imagine that most packages, I would imagine Python and R just have built-in packages to do a lot of this work for us. And what we're going to be focusing on in this book is probably understanding how to interpret outputs. Okay, I think we're comfortable with algorithms, right? It's just a recipe. It's a step-by-step process on how we do stuff. That seems fine. Have a look at figure 1.1. Add an algorithm I made for making a cake. Okay. Here's the cake algorithm. How'd they do? Oh, fuck, you clipped it. There's also the book Elements of Statistical Learning, also free on its website. Is that the one we have? No, I think they have Introduction to Statistical Learning, right? On its website. So yeah, I guess we can pop it over into that. Make sure I'm on a new tab so you're not seeing my stuff that you're not supposed to see. Yeah, that's the goal, Addy, is I want to be able to kind of use this as a jump off space for us to actually do some work. So elements of statistics. Cool. Download the PDF. That's what we want. And then we'll just throw that into the resources. Hi, Obi, how you doing? Boom. Okay, we'll let that download while we're reading. So, start. I love how they have a start. Start. Mix ingredients. Well, what fucking ingredients do they want? Put cake in, bake for 20 minutes. Test with fork. Ready, not ready. So there's a dichotomy. Either it's ready or it's not. Sure, bake for another 5 minutes and test again. So there's a loop down here, right? We kind of keep going through this loop if it's not ready. So we just keep baking for 5 extra minutes. Past the 20 if it doesn't work. If it's ready, we move over here. We decide on an accompaniment. Ooh, prefer ice cream or prefer custard? Custard's gross. I'd probably go for ice cream. Add ice cream. Serve cake. What? Erg raisins? Where did that come from? If it's good, we end. If there's raisins in it, apparently we go back and we mix the ingredients without raisins? With raisins again? I get the sentiment here, but it's a little lacking in extra content. Anyway, sometimes there are decision points where the route we take depends on the current state. Sure. Or we need to go back and iterate something. Yeah, that's fine. So we might have to use control statements is what I'm thinking, right? Okay, so they've explained what an algorithm is by baking a cake. Seems reasonable. Having gathered data on your patients, you train a machine learning algorithm to learn patterns in the data associated with the patient's survival. So in other words, we're going to have a data set that probably contains a bunch of variables and then whether or not the patient survived or died. Exactly, Addy. This is totally an algorithm for infinite raisins. This is an algorithm for infinite raisins. All you have to do is just continue to say, erg raisins. Do I have a...
Bruh.
So many raisins. Who likes raisins? Does anyone here really like raisins? Oh, this is a super informal class, Obi, don't worry. This is just me learning about machine learning. And I have to run to a meeting with the registrar right after this. We're in the middle of scheduling. I have like 6 grade appeals that I have to deal with, so I wanted to dress in my usual college attire for that, let's say, so I don't have to do that after stream. You guys always see me like when I'm like super late at night or like in the afternoon after I've done all of my work stuff. And I'm just like, all I want to do is wear a sweater all night. Okay, as another example, imagine you work for a power company and it's your job to make sure customers' bills are estimated accurately. I've always kind of wondered about this. They must use time series data for that, don't they? I've always wondered about that. Only that I do love chocolate-covered raisins, actually. Oh, man. You can spin the wheel of show in the middle of the lesson for maximum chaos, true. I will not stop you. Because mostly what I'm going to be doing is probably reading and coding, right? And this... I feel like a lot more of the discussion is going to happen in between, right? We have downloaded that new thing, so let's upload that file. Should be here. What is this book called? Elements of Statistical Learning by Hasty? Stop being so hasty. There, we'll add that as a resource as well. Whoop. Yeah, so you train an algorithm to learn patterns of the data associated with the electricity use of households. I feel like that must be a time series, and you're just kind of like forecasting. When the new household... Oh, I see. When the new household joins the power company, you can estimate how much money you should bill them each month. So they're thinking about it probably differently from how I would think about doing it. But one possible solution. Okay, that makes sense. Finally, imagine you're a political scientist. God, this is not the right time to talk about political scientists. I saw the best meme today, and I kind of want to show you. If I can. I don't know if I can. I'm gonna have to turn my... Okay, let's see if I can do this. It was like in response to all the fucking shit that's happening, like politically. Hello? I just had, that made me laugh so hard today. I was like, yes, this is literally me every morning when I wake up. Anyway, you're a political scientist and you're looking for types of voters that no one including you knows about. What? I know, it's got such a good beat to it, Martin. Such a good beat. That's the question we want to answer, Addy. If you find it, please post it under memes in the elements. I would much appreciate it. So you train an algorithm to identify patterns of voters and survey data to better understand what motivates people. Sure. Okay. So this all seems pretty reasonable. You know, this is stuff that I've seen students do in presentations before. But we haven't really seen any nuts and bolts yet. So here's an example, I guess. Oh, they first used the term machine learning in 1959? Why is it so popular now if it was coined in 1959? He used it to describe a form of AI that involved training an algorithm to learn to play the game of checkers. Oh, okay, the word learning is what's important here, as this is what distinguishes machine learning approaches from traditional AI. Traditional AI is programmatic. In other words, you give the computer a set of rules so that when it encounters new data, it knows precisely what output to give. Okay. An example of this would be using if-else statements to classify stuff. Okay. We can look at the R code. I don't think it's going to be super insightful. I think it's going to be very straightforward. So we have a vector that contains the number of legs of 3 different objects, 4, 4, and 0. And then we have a vector that is a true-false vector, I guess. Like a... what's the word I'm looking for? This will be like numeric, and this will be... It's not binary. What is this? Logic? It'll be like a logical vector, right? Where it just contains trues and falses. So I assume everything's ordered. And it says, go through all of the items. Well, actually, maybe it'll be better if I can do this. What? That's not what I want. There you go. You got a bird's eye view of my house. Now you can take with that whatever you want. Do with that as you wish. Look me up on Google Maps. So we have a vector that contains 4, 4, 0. We have a vector that contains true, false, true. And then we have this for structure, this control structure. It's going to go through each piece. So I in 1 to 3. So here's like 1, 2, 3. And it does an if statement. So if number of legs 1, 2, 3 is identically equal to 4, then do some stuff. So obviously we return back accurate move forwards here and not accurate move forwards here. So when I is equal to 1, we have that number of legs is equal to 4. So it's going to move into this second part of the third part of this control structure. It's going to go into this next nested if. If climbs tree I, if climbs trees I, what? There must be a mistake here. I think there's a mistake, right? Don't we need equals true? I think what they're trying to imply is there's objects that have 4 legs that can climb trees, there's objects that have 4 legs that can't climb trees, and there's objects that have 0 legs. Number of legs 0 but can climb a tree? Oh, I see. Does it automatically register it? Hey, you know what? Let's open up R because now I'm kind of curious. Do we need to tell it true, or does it automatically assume a binary choice? I should be able to copy and paste this, I think, right? Okay, cool. A lot of programming languages just default to true. I see. So that's what I just want to check. I suspect that based on your conversation, that's what R is going to do. But as an individual that knows there's more than one choice. Huh? Well, actually, let's just clear all the other stuff that's in here that is going to bust stuff up on us. So, fine. That's fine. Okay, cool. So it does print out what we need. It does assume that 1 is true because it will come back to this one because we've already moved forward in the if statement. Okay, cool. So I did not know that. I learned something new today. So that means it's doing something like this. So it starts here in the for statement. It starts with I is equal to 1. Then it goes into number of legs. It checks that first numerical value, which is 4. It's equal to 4, so it's going to move into the second if statement, and it's going to check to see if it's true or not. We know it's true, so it returns back cat. Makes sense. It'll do the same thing for when I is equal to 2, so I is equal to 2, number of legs is 4. If this is true, print cat, otherwise print dog. So it's false this time, so it prints dog. Else print snake. Oh, a snake has 0 legs. Oh, okay, so a snake has 0 legs but can climb trees. Okay, that's fun. Yeah, so we verified that on R, that makes sense. Hey, Famished, how's it going? Also, hi, Ryan. Welcome in. So just normal programming stuff? Yeah, it's been a while since I've done actual, like, good, solid programming. My apologies. Currently setting first-order logic, which also has the notion of predicated and functions, among other... Oh, predicates and functions. Yes, that was a very simple classifier based on 2 features. That's correct, yeah. Weekends for math and programming, and the week for programming and psychology. Ooh, nice. Well, if you ever need to spend some time programming with us, we're going to be doing that probably on Fridays. Okay, so they're saying that this is problematic because obviously there's more than 3 animals. So the number of entries that we would need in here would be a lot, right? And there might be more than just 2 nested if statements, the more and more items we get inside of those 2 vectors, yeah. So we contrast this with the machine learning approach, where instead of telling the computer the rules, we give it the data and allow it to learn the rules for itself. The advantage of this approach is that the machine can quote-unquote learn patterns we didn't even know existed in the data. And the more data we provide, the better it gets at learning those patterns. Okay, cool. So data and rules passed into traditional AI will give us answers. So we create the algorithm by specifying the rules. That's what the last example was showing us, right? Then traditional AI can give us the answers based on the rules. Got it. For machine learning, they're saying we give data to an algorithm. Either we also give it the answers or it learns them for itself. So we could provide the answers or we could not provide the answers. Is that the difference between supervised and unsupervised learning? I'm trying to remember. Okay, so we throw that into the machine learning algorithm and then it pops out rules that map answers to data. Yeah, okay. Anyone know if stream will be uploaded to YouTube or saved as a VOD? Yeah, we can probably upload these to YouTube. I think so. That should be fine. They will be certainly available as VODs on Twitch. Absolutely. And those last for about 2 weeks. But I think adding them to YouTube is a good idea. The difference between a model and an algorithm. Is there a difference between a model and an algorithm? I mean, a model could probably contain more than one algorithm. In practice, we call a set of rules that a machine learning algorithm learns a model. Once the model has been learned, we can give it new observations and it will output its predictions for the new data. We refer to these as models because they represent real-world phenomena in a simplistic enough way that we and the computer can interpret and understand. Just as a model of the Eiffel Tower may be a good representation of the real thing, but isn't exactly the same. So what the hell's a model?
Zeta! Transforming Ra into an AI? Brilliant algorithmic concept. Let's calculate the potential. What's the main function of this creation? Time to calculate. So... Katawawi.
So Katawawi. Model is a really complex function. So they're kind of just saying that a model is the set of rules that a machine learning algorithm learns. Too many learns. Okay, let's not get too caught up on that. Okay, so the process by which the model is learned is referred to as the algorithm. Hopefully that'll become a little bit clearer as we work on something. As we discovered earlier, an algorithm is just a sequence of operations, right, working together to solve the problem. Say we have 2 continuous variables and we would like to train an algorithm that can predict one given the other, right? So we have a dependent variable. We want to predict the dependent variable given the independent variable, right? Or we want to predict the outcome given a predictor. The relationship between these variables can be described by a straight line that can be defined using only 2 parameters, its slope and where it crosses the y-axis, right? So mx plus b form. Sure. Any straight line can be described by its slope and its intercept. The equation y equals intercept plus slope times x can be used to predict the value of y given something, right? So an algorithm to learn this relationship could go something like the example in figure 1.4. We start by fitting a line with no slope through the mean of the data. We calculate the distance each data point is from the line, square it, right? And sum these squared values. The sum of squares is a measure of how closely the line fits the data, right? Next, we rotate the line a little in a clockwise direction and measure the sum of squares for this line, right? If the sum of squares is bigger than it was before, we've made the fit worse. If we rotate the slope in the other direction, so we rotate in the other direction and try again. If the sum of squares gets smaller, we've made the fit better. Gotcha. Okay, that makes sense. We continue with this process, rotating the slope a little less each time we get closer, until the improvement on our previous iteration is smaller than some preset value. Typo. We've chosen. No, maybe it's not. It just looks like there's a really big space right there. The algorithm has iteratively learned the model, needed to predict future values. Is that how least squares works? Is it just all by rotations? You're gonna turn Reese into an AI? I mean, Reese has a very simplistic machine learning model. If my head is on your laps, then pats. If my head is not on your laps, then sleeps. If hungry, food. Very simple. Very simple. I hope we get to think about neural nets. I really want to look at neural nets this summer. So Ryan is saying, I'm not in the position to critique this book, but the book Artificial Intelligence and Modern Artificial Norving has a better, more sophisticated general philosophical introduction of what a model is and why it's often also a function from some chosen function space and the associated principles. Is that available online in some capacity, Ryan? So if they're, as we're discussing things, I'm specifically choosing the textbook that my institution uses as the introduction for machine learning, but I'm happy to look at other sources while we're together during these streams. So if you would like to, there's a machine learning resources forum or a post in the forum. You can add whatever resources you think are appropriate here. So if that source is kind of free to read, right, in some capacity, post it in here and we can take a look at it. Because yeah, I'm not opposed to looking at the more mathematically directed concepts, because it sounds like a function space kind of problem, which I think would be really interesting to see how the math and stats kind of connects to some of the more pure mathematics topics that I know fairly well. While certain algorithms tend to perform better than others with certain types of data, that makes sense. No single algorithm will always outperform all others on all problems. Well, yeah, of course. This concept is called the no free lunch theorem. That's a theorem? Seriously? Stop. That cannot be true. It's a theorem. Oh my god. In mathematical folklore, it's not even in mathematics, it's in mathematical folklore. The no free lunch theorem alludes to the saying, no such thing as a free lunch. That is, there are no easy shortcuts to success. It appeared in 1997, no free lunch theorems for optimization. Wolpert had previously derived no free lunch theorems for machine learning. That's funny. That's actually really funny. I like that it has an abbreviation, the NFL theorem, yeah. I'm going to text that to my group chat. Do you guys know about the NFL theorem? Where's my group chat? Okay, well that was a fun little sidetrack. Okay, so Martin says yes, I've heard of that. Okay. In other words, you don't get something for free. This is, the algorithm takes the predictor and outputs variables. This must be the slope intercept one we were looking at. So it says start, fit horizontal line through the mean of data, right? Save square distances as initial. Increment the slope clockwise. Save square distances as new. Is new less than initial? If yes, is the improvement less than a preset value? Yes, we end. If new is not less than initial, so if it's bigger than or equal to, it goes into increment the slope counterclockwise, find the new square distances, and then just kind of repeat this process. So is the improvement less than a preset value? No, I see. Then it goes back and reiterates using the initial new structure again, right? So it saves this new one as initial, and then we go a little less and go through the process again. Yeah, okay, that seems fine. So here's a little visual of what they're doing. Iteration 100. So that's kind of cool. I didn't know that's... I kind of got the sense that they used an X mean or a Y mean, but I didn't realize that it was about kind of like tilting and... that the least squares algorithm was about rotating, double checking, rotating, double checking, rotating, double checking. So I think that's interesting. So data scientists typically choose a few algorithms they know tend to work well for the type of data and problem they're working on. So maybe that's another thing that we should try to get as an end goal to this. If we're working on specific kinds of problems, what kind of algorithm should we use to approach a particular problem? So maybe there's a handful, right, like one or two that we might want, maybe two or three that we might want to test out on this particular data set. And then I guess we work through all two or three of those and try to figure out which one has the best model, right? Oh, here we go. Classes of machine learning algorithms. This was a question that I had. Machine learning algorithms can be categorized by their learning type and the task they perform. There are three learning types: supervised, unsupervised, and semi-supervised. The type depends on how the algorithms learn. Do they require us to hold their hand through the learning process? That would be supervised, I guess. Or do they learn the answers for themselves? Unsupervised. Supervised and unsupervised can be split into... Oh, okay. So regression and classification tend to be supervised learning. Clustering and dimension reduction tend to be unsupervised learning. Okay. So what would make regression, for example, supervised learning? What makes that a supervised learning algorithm? AGI GTFO theorem? What? I know the hairy ball theorem is like one of my favorite theorems to talk about. So I'm trying to think of like, how is regression different from clustering? Clustering is like, I'm trying to kind of like get a general sense of why that's the case. So like clustering, what we're going to do is we're going to throw all of our data down. And let's say we're doing like k nearest neighbors or k means. So what makes that unsupervised? We don't have an answer, right? The algorithm has to learn the answer, right? So the output that we get from k nearest neighbors or k means comes from the model looking at the data and processing it up to a certain parameter that we've probably chosen, right? Making clustering supervised would mean giving the correct groupings. Right, so we would need to give it the answer, which we actually don't know, right? But in regression, we do know the answer, right? Like given a set of data, we can theoretically create a regression model very quickly. Yeah, and classification is discrete, yeah, rather than continuous. So I guess the idea is for classification and regression, given some kind of input, we actually do know what the output's going to be, right? We do know the answer to the question. But something like clustering or dimension reduction, right? Which dimensions are the most important? We actually don't know what the answer is. We're actually asking the algorithm to do that for us. Okay, I think I kind of get it. It'd be nice if this was explained a little bit more, but again, we'll probably see it a little bit more as we get deeper into the book. Okay, so we classify algorithms on how they learn and what they do. Fine. Differences between supervised, unsupervised, and semi-supervised. Imagine you're trying to get a toddler to learn about shapes by using blocks of wood. In front of them, they have a ball, a cube, and a star. You ask them to show you the cube, and if they point to the correct shape, you tell them they are correct. If they are incorrect, you burn them. You also tell them. You repeat this procedure until the toddler can identify the correct shape almost all of the time. This is called supervised learning because you, the person who already knows which shape is which, are supervising the learner by telling them the answers. Got it. Now imagine a toddler is given multiple balls, cubes, and stars, but this time is also given 3 bags. The toddler has to put all the balls into one bag, the cubes into another bag, and the stars into another. But you won't tell them if they're correct. They have to work it out for themselves from nothing. But the information they have is in front of them. What? That doesn't make any sense. Doesn't this have an answer? Isn't that the answer we're looking for? All of the balls in one bag, all of the cubes in the second bag, and all of the stars in the third bag. Isn't that an answer? But you won't tell them if they're correct. I see. But how do they know when to stop? So you're saying the toddler does not know which objects are the balls, the cubes, or the stars. It needs to compare them. Yeah, see, I know. There's some really funny memes, Obi, with like all the like different sized blocks, and it's like, where does this one go? Where does this one go? And then they all end up going through the same square, and like the person's face gets like sadder and sadder. They stop when they get sufficient. So there must be more to this, right? Like there must be more to this because I guess like us as the analyst or the scientist, we're going to look at the output that comes out and we're going to go, that's a load of garbage. Or yeah, this seems reasonable, right? Like I guess that the onus is on us, not the toddler, to look at the output and see if it makes sense. But maybe, I don't know, do we need to know what these are? I guess maybe that's what's hard, right? Like, I don't think we as the data scientists actually know how to label these objects, right? The toddler's just going to take all this stuff, put them into different bags, and we're going to look at the output and go, does that make sense or not? And if it doesn't, maybe we reiterate. Yeah, like, that's what it feels like to me, Addie. Like, it feels like if it's supervised, we know what these things are, right? And where they need to go. But if it's unsupervised, I feel like we don't really know what the answer is, so we're just kind of looking at what we're given to us from the toddler, these 3 bags, and we got to make a judgment call. Does this make sense? Does this not make sense? What do we think? Sometimes we kind of know, but sometimes we do not, and just discover it from scratch. Okay. I don't want to spend too much time. I think these are like weird. These feel like super weird, intuitive examples. I'm hoping that when we actually work on an algorithm, things will be a little bit clearer. Okay, so we've talked a little bit about this. Another example would be if we were trying to estimate a person's monthly credit card expenditure. We could give an algorithm information about other people, such as their income, family size, whether or not they own their home, including how much they typically spend on their credit card in a month. Right. The algorithm looks for patterns in the data that can predict these values in a reproducible way. When we collect data from a new person, the algorithm can estimate how much they will spend based on the patterns it's learned. So this feels like we've already created some kind of model. We're adding a new data point into the model, and we're getting output based on the model that we've already created. That's what it feels like. So we already know the answer. So that's supervised. Machine learning algorithm is unsupervised if it does not use a ground truth and instead looks on its own for patterns that hint at some underlying structure. So let's say we take gene expression data from lots of cancerous biopsies and ask an algorithm to tell us if there are clusters of biopsies. A cluster is a group of data points that are similar, but different from data in other clusters. Yeah. This analysis can tell us if we have subgroups of cancer types that we may need to treat differently. Right. Okay, I can see that. We may have a data set with a large number of variables, so many that it's difficult to interpret the data and look for relationships manually. Okay, we can ask an algorithm to look for a way of representing this high-dimensional data set in a lower dimensional one, while maintaining as much information from the original data as possible. Dimension reduction. Take a look at 1.5. If your algorithm uses labeled data, then it's supervised, and if it does not use labeled data, then it's unsupervised. Okay, I feel like I'm a little lost on what they mean by labeled data and not labeled data. Maybe this will help. So we give it fully labeled data. A supervised algorithm will output a model for us. Right, and then new data that we haven't labeled yet. Right, okay, so we have to pick a characteristic, right? So we feed in a data set to an algorithm, it pops out a model. Now I have this new data point that's not labeled in a particular column. I put it into the model and it gives me a predicted value. That's supervised learning. Okay, that feels like it makes sense. Oh, I see. So this has not been labeled. Oh, okay. So there's a characteristic that hasn't been labeled yet. We pass unlabeled data into an unsupervised algorithm to get a model. And then we can put new unlabeled data into that model, and it should tell us how it maps into the thing. Yeah, okay. Okay, I think I understand the difference now. It must be like when they say labeled data, it means that we know what the outcome is for a particular characteristic, I think. And when they say unlabeled data, it means I don't know what the outcome is for a particular characteristic. For example, I don't know, if we're looking at the data on bone biopsies, right, cancerous biopsies, right, we have a cluster output, right? Cluster 1, cluster 2, cluster 3, etc. And then we're going to bring new data into that model, figure out how it maps into this new cluster. Okay. And then maybe update the model as needed. So, okay. I think I kind of get it, what they're trying to say here. Label equals answer. Yeah, okay. You think of the table representation of a function. So some insight into this figure before I go to sleep. An algorithm is a mathematical function that maps from the set of all possible data sets to the set of all possible models. So input one data set and it will spit out one model. That's the difference between algorithm and model. Okay, algorithm is the function on the set of all possible data sets. Gotcha. So domain is data sets, output is a model. Right, okay. Thank you, Martin, that makes a lot of sense.
Huh, nicely integrated.
I'm not even going to look at semi-supervised learning because I just want to figure out what the what supervised and unsupervised learning are first. Okay, so this is going to maybe go into some of the introductory topics that I personally want to get a little bit of a better sense of how they work. So classification, regression, dimension reduction, and clustering. These are the four biggies that I definitely want to take a look at this summer. I know a decent amount of how regression works. I know a little bit about how the others work. And probably the one I know the least is dimension reduction. So I feel fairly comfortable with regression, although I'm curious to see how they approach it from a machine learning perspective. I feel like classification won't be as challenging knowing how regression works. It's just the discrete case of that, I believe. So that's probably done with like decision trees or something like that. I'm familiar with KNN and K-means clustering. And I'm the least familiar with dimension reduction, so I'm super excited to kind of to revisit these and learn a little bit more. Okay, so our classification algorithms take labeled data and learn patterns in the data that can be used to predict. Yes, that makes sense. This is most often a grouping variable and can be binomial or multinomial. Classification problems are very common machine learning tasks. Which customers will default, which patients survive, which objects in a telescope image or stars, planets or galaxies. Right. So if I'm trying to, so let's see if this makes sense. So will the patient survive? That would be like a binomial classification, right? It's either yes or no. We're looking for an answer and it's yes or no. If I do something like this, which objects in a telescope image are stars, planets, or galaxies, now I have three possible outcomes. That would be multinomial, right? More than two groups. So I think that makes sense. I'm okay with that. Regression algorithms take labeled data and learn patterns in the data that can be used to predict a continuous output. Yes. How much carbon dioxide does a household contribute to the atmosphere? What will the share price of a company be tomorrow? What is the concentration of insulin in the blood? Right. Okay, I feel like most of us are probably familiar with that kind of algorithm. So dimension reduction algorithms take unlabeled and high dimensional data, so many variables, and learn a way of representing it in a lower number of dimensions. Dimension reduction algorithms may be used as an exploratory technique or as a pre-processing step in the machine learning pipeline. It can help mitigate problems such as collinearity and the curse of dimensionality. What? What's the curse of dimensionality? That sounds terrifying. I'm gonna put the curse of dimensionality on you, chat. Dimension reduction together with statistics and representation learning is super interesting. I want to know. I want to know. Oh, have a good night, Martin. Sleep well. Dimension reduction is an eliminate student ID from this dataset because it shouldn't matter for final exam grades. Yeah, so the eigenvalue in the direction of student ID would not accurately predict final exam grades, so the dimension reduction would probably remove that. I kind of want to know what the curse of dimensionality is right now. Curse of dimensionality. Does anybody have any guesses? My guess is that it probably has something to do with computing power of working with lots of parameters. So the more dimensions that we have, the more computing power it's going to take to do something. It's probably something like that. The curse of dimensionality refers to various phenomena that arise when analyzing and organizing data in high-dimensional spaces. The curse generally refers to issues that arise when the number of data points is small relative to the intrinsic dimension of the data. It was definitely not what I thought. Oh, here we go. So machine learning, problems that involve learning a state of nature from a finite number of data samples in a high-dimensional feature space, with each feature having a range of possible values. Typically, an enormous amount of training data is required to ensure there are several samples with the combinations we need. Yeah, right. In an abstract sense, the number of features or dimensions as the number of features grows, the amount of data we need to generalize accurately grows exponentially. Ah, that's the key. Okay. So it does have something to do with... It has something to do with, so as we start adding more dimensions, or as we start adding more features, columns to our data set, in order to train things appropriately, we need to grow exponentially the number of data points that we have. So it does have something to do with computing power. Okay, clustering algorithms take unlabeled data and learn patterns of clustering. A cluster is a collection of observations, right, that are more similar to each other than the other data points. Yes. And the same clusters share some unifying features that make them identifiable from other clusters. Sure. May be used as an exploratory technique. Yes, so this is how I typically use it. Clustering algorithms may be used as an exploratory technique to understand the structure of our data and may indicate a grouping structure that can be fed into classification algorithms. Right. Are there subtypes of patient responders? How many classes of respondents were there in a survey? Do different types of customers use our company? Right. When faced with problems like these, you should use a clustering algorithm. So in our marketing data analytics, we use clustering quite a bit. Drua, hello. Are we learning machine learning by reading literature novels? We're learning today. I'm just doing a little overview, I guess, an introduction, trying to learn some of the terminology. I don't know how in-depth this book is going to go. But we also have some other sources we can explore for some of the more mathy concepts, the more mathy things. Like this one goes through like... This is definitely like stats lingo. Some function of an unknown variable plus epsilon. I'm like, yeah, that definitely looks very statsy to me. Like, they just jump right into it. They're just like, fuck it. We're going to do linear regression on page 16. But I wanted kind of a more general overview of how to classify stuff, like where stuff lands, how we think about supervised versus unsupervised. There's a lot of terminology that I don't know, and I'm trying to get a better idea of what all these words mean. So they just say, they've basically given us a control structure here, right? If you need to predict a categorical variable, use classification. If you need to predict a continuous variable, use regression. If you need to represent the information of many variables with fewer, we use dimension reduction. And if you need to identify clusters, we use clustering. Makes sense. Yeah, deep learning. And you may have even heard the term in media. Deep learning is a subfield of machine learning. Okay. It can produce models with outstanding performance. Okay. I mean, they haven't really defined what that means. We now have the computational power to apply it more broadly. Okay, so deep learning uses neural networks to learn patterns in data. Okay, so neural networks are connected to deep learning, which is a subfield of machine learning. Okay, we've already looked at that. So we don't typically use deep learning because they're computationally expensive. That makes sense. they tend to require more data, so this must be the curse of dimensionality that they're talking about. The rules are less interpretable. What does that mean? By their nature, deep learning models favor performance over model interpretability. Oh, okay. So our focus should be on, arguably our focus should be on performance, but often we're not only interested in getting the right output, we're also interested in the rules the algorithm learned because these help us to interpret things. Yeah. The rules learned by neural networks are not easy to interpret. Okay. The ethical impact of machine learning. I don't know if we care about that. Why use R for machine learning? I mean, R or Python, I don't particularly care. Which data sets will we use and what will we learn? Okay, so that pretty much pops off chapter 1 for us. Now, I am curious about this third textbook that we opened up. Is that this one? Let's take a look at the contents. I think what I'm going to do next week is we want to pop into kind of our first machine learning algorithm. So let's take a little bit more of a look at what they're going to be doing in Chapter 2. We might be able to just skip Chapter 2. It says tidying, manipulating, and plotting data. So it's up to you guys. I'm fine if we skip over Chapter 2, unless you want to learn a little bit more about the tidyverse in R. But I feel like we're all going to be probably coding in different languages. That'd be my guess. I'm not opposed to like skimming through Chapter 2, but I might do that during the week. Because I think what I want to do is I want to start into Chapter 3 next Friday. Like, we might as well just like get right into classification model and just start building some models. I think that will be fun. So let's tentatively skim through Chapter 2 during the week. I will probably have a stream on that at some point, just so that I just want to look at it and see what it says. And then next Friday, we'll actually read through Chapter 3, and hopefully we'll be able to start actually building a model, a classification model, and just start seeing what it does. I want to learn about this kind of, the idea of like taking a data set and breaking it up into training, testing, and things like that. So I want to like actually start like doing some of that coding, so I get a better sense of how it works. What language I'm going to write in R, probably, because that's what I'm most comfortable with. Probably R with a little bit of help of ChatGPT. But I know that there's some other folks in the server that want to use Python, and I have Python on my computer, so I'm open to doing both. You should be code agnostic, yeah. Quite good at clusterfuck detection. What? So let's put that on the agenda. I'm just going to throw that in the announcements. So what's it going to be? So schedule for this week. We're going to skim through Chapter 2 of Greece. Friday. Friday 11, we will do Chapter 3. And let's take a look at what's going on in these other two sources that we have. So what are they trying... Okay, I'm just trying to get a general sense of like what they're trying to do in their introductory chapters. And maybe there's something we can do for like the next 20 minutes or so before I have to pop off. This might not be bad, this like introduction. So this is talks about statistical learning. Oh, it has a lab introduction to R basic commands, blah, blah, blah. And then it goes into linear regression and then classification right after that. I get we can probably jump around chapters in this particular source. This is the James text. And this was the other one that was suggested to us. This was the Hasty text. So overview of supervised learning. This looks like... This looks good too. What do I want to do for the next little while? What makes sense? I think maybe I'm just going to kind of take a peek at the James text and just kind of see what they're doing in chapter 2 here and see if we can glean anything interesting from chapter 2. The intersection of those two books are non-empty, probably. If I'm feeling motivated, try to map the sections of Reese onto the other books. It shouldn't be too hard for us. I don't think. I think the other two books are just going to give us a bit more of like a mathy look at what Reese is going to do, which is why I think they're going to be good resources. And I'm a little hesitant to like jump into something knowing that I have to like leave in a half an hour to get to the college. But I mean, we can maybe take a look at the introductory chapters. Classification is going to be supervised learning for us, right? So maybe let's take a look at this introduction here. So in order to motivate our study of statistical learning, we begin with a simple example. Suppose we are consultants hired by a client to investigate the association between advertising and sales of a product. The advertising dataset consists of the sales of that product in 200 different markets, along with the advertising budgets, okay, in TV, radio, and newspaper. The data are displayed in figure 2.1. Ah, I see. So TV, radio, newspaper, we have the sales along the y-axis. Maybe in millions or something like that. Oh, wait, in thousands. Okay, and each one of these dots represents one of the 200 different markets. In each plot, we show the simple least squares fit of sales to that variable. In other words, each blue line represents a simple model that can be used to predict our sales, right? Since we're working with a continuous kind of variable, sure. It is not possible for our client to directly increase sales of the product. Yes. On the other hand, they can control the advertising expenditure. Yes. Therefore, if we determine that there is an association between blah, 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 yeah. Our goal is to develop an accurate model that can be used to predict sales on the basis of the 3 media budgets. Right. So X1, they're going to call the TV budget, X2 the radio, X3 the newspaper budget. Okay, and they have just some terminology there I'm not too fussed about. So more generally, suppose we observe a quantitative response Y and P different predictors, X1 to XP. We assume that there is some relationship between Y and the set of X's, which can be written in the general form. What are they implying here with F? So F acts on all of this to get an output, right? Yes. Okay, so F is acting on this vector. We're going to get some output, and there's going to be some kind of potential variation, right? So, right, okay. I think I understand what they're trying to say. So here f is some fixed but unknown function, right? Multivariable function. And epsilon is a random error, right? That's our error term, which is independent of x and has mean 0. Yeah, so this is just a typical linear regression kind of thing, right? So, okay, so consider the left-hand panel in 2.2, a plot of income versus years of education for 30 individuals. The income data set, left. The red dots are the observed values of income in thousands of dollars and years of education. So years, the number of years affecting thousands of dollars is our income. Okay. For 30 individuals. The blue curve represents the true underlying relationship between income and years of education. Sure. Which is generally unknown, but it is known in this case because the data were simulated. The black lines represent the error. Note that some errors are positive, some are negative. Yes. Overall, these errors have approximately mean of 0. Is that an assumption that we have to make on this kind of model? Hi, Waffle. How are you doing? Welcome in. Reese is on the floor right now. Yeah, he was on the couch. Bye, Addie. Yeah, we're going to be winding down here pretty soon. Is anyone actually online that we can raid into? Doesn't look like it. Okay, so nothing super exciting here. Why estimate the function? So in this chapter, we outline some of the key theoretical concepts that arise in estimating f, as well as tools for evaluating estimates. So this must have been what Martin is talking about, right? Like f is the function that we're trying to estimate that acts on the data set to give us the output y. So there are two main reasons why we may wish to estimate f: prediction and inference. Right, so prediction, in many situations a set of inputs are available, but the output y cannot be easily obtained. Sure. In this setting, since the error term averages to 0, we can predict y by predicting the model, right? Yeah, so f hat is the estimate for our model. And y hat represents the resulting prediction for y. Yeah, right, so estimate, prediction. I have no idea what that sentence means. Let's just not worry about it. As an example, suppose that x1 to xp are characteristics of a blood sample that can be measured. Y is a variable encoding risk. Okay. It's natural to seek to predict y using our dataset x, since we can then avoid giving the drug to patients who are at high risk. Right. So the accuracy of y hat as a prediction for y depends on two quantities, which we call the reducible error and the irreducible error. So in general, f hat will not be a perfect estimate, correct? And this inaccuracy will introduce some error, yes. This error is reducible because we can potentially improve the accuracy of f hat by using the most appropriate statistical learning technique to estimate f. So what's the irreducible stuff? Even if it were possible to form a perfect estimate so that our estimate response looked like this, our prediction would still have some error in it. That's because y is also a function of epsilon, right, which by definition cannot be predicted using x. Therefore, variability associated with epsilon also affects the accuracy of our predictions, right. That's the irreducible error. So there's the error that we can fix by choosing a better model, and then there's the error that's just ingrained in the overall equation, I suppose, right? Right, so no matter how well we estimate the function f, we cannot reduce the error introduced by epsilon. Okay. So the quantity epsilon may contain unmeasured variables that are useful in predicting y. Quantity epsilon may also contain unmeasurable variation, right? So they're just saying it's a positive value. So consider a given estimate f hat in a set of predictors x, which yield the prediction we're looking for. Assume for a moment that both f hat and x are fixed. So that the only variability comes from epsilon. So what are they doing here? They're saying, well, y is really just f of x plus epsilon. And then the predicted value is really just our estimate for f evaluated at x. And this is a squared expected value. Okay. I'm not a statistician, but I probably should know how this works. So they're saying that the expected value of this... Okay, let's just copy this and paste it and see if we can do some actual math before I have to leave. Is this easy to talk about? Is the expected value of some error really just the variance of the error? Hey Rex, how you doing? Yeah, anyone can go fishing lawful. You just have to type !fish. So what are our expected value rules? I guess that's what we have to look at. Expected value rules. How you doing, Rex? Okay, properties. Yeah, so this is what I was kind of... Oh, but we're working with an expected value squared.
Darkness.
That scared me a little bit. Hi, Zach. How are you? There must be... I know there's some formulas that I probably proved forever ago about how to work with squared expected values. So we're looking at the expected value of something... Oh, wait. The expected value of something squared. I can square that thing, can't I? Can't I just take this? Oops. Square it. Oh, this is going to be annoying. Maybe that's too annoying. There must be an easier way to do this. I can just bring this... That's a singular thing, though. Yeah, those are fine. So expected value is linear. I know that. But how do I deal with these squarey things? Okay, so they actually do it by squaring it. And then using the linear property of expected value. Okay, so maybe we should actually just square this. So let's go f plus epsilon minus f hat. Let's square this and see what we get. So we would get f. I have to be a little careful here. It's not f squared. It's actually f squared like this, right? It's actually f evaluated at x squared. So I'm being a little loosen with my notation here, but epsilon f minus f hat, and then we'll get an epsilon f, an epsilon squared minus this. We'll get a minus this. Does anything cancel? It just looks like I get 2 copies of a bunch of stuff. So I get like fx squared plus 2 copies of this. That'll do these. Minus 2 copies of these. That should take care of that. Minus 2 copies of this. Epsilon f hat x. Takes care of that. And then we have the other business. So plus our epsilon squared and plus our f hat x squared. Now they're saying some of this reduces down to f of x minus f hat x all squared. Plus the variance of the error. Nope, that looks like it's probably a helpful thing. That's for a random variable, though. Can we think about the error as a random variable? Like, would the variance of epsilon be equal to the expected value of epsilon squared minus the expected value of epsilon all squared? I'm also trying to figure out, like, where does this come from? So this is the statement. So we have a predicted model for, so y, capital Y is a function applied onto a vector plus the error, and we have the predicted model, y hat, is our estimated f hat evaluated at that same vector. And so this equality I'm fine with because they're just taking the 2 y values and inputting them. It's the second equality that I'm having a little trouble seeing what they're doing. Like, how are they, like, where does this expected value go? Right, and they've used that sneaky phrase, it's easy to show. It is easy to show. So I know that it's not easy because I haven't taken statistics in forever. And I don't know what I am and am not allowed to do with these things, right? So I've kind of expanded this out just to see if I could use... So I can certainly use linearity of expected value, right? Like, I know that I get something like the expected value of fx squared I assume epsilon is some kind of... Wait, is epsilon... That's what I don't know. I mean, I feel like this epsilon value is going to be dependent on capital X. No, it's not dependent on capital X. They said that, right? It can't be dependent on capital X. Yeah, y is a function of epsilon, which by definition cannot be predicted using x. But it's not a constant though either, right? So how does expected value work with these error functions? And there is indeed a concept called variance of an estimator. Okay, let's take a look at Zach's thought, which is straightforward to me. So I'm not exactly sure how to deal with this epsilon thing, so I'm just going to call it expected value of the stuff I don't know how to deal with, and I'll put that at the end. But I mean, certainly we should be able to do this, some of this stuff, right? Like I can do 2 expected value of this, and then plus expected value of this. That I feel comfortable with. And then there's all this other stuff I just don't know how to think about yet. So it's going to be all of this epsilon-y stuff I'm not really sure about. So is that true? Does all of this come out to be that? Yeah, so f squared minus 2f f hat plus f hat squared. Okay. So I can see that. That makes sense. So, but where does the expected value go? So sure, we can collapse all these things. I see how all of that is connected to this particular term, but why is there no expected value here? Like, it's almost like they just dropped the expected value brackets and they're like, bye! And then somehow all of this has to deal with the variance? Oh, you're right. They actually did say that x is fixed here. So it's, if x is fixed, then the expected value of the thing is just the thing. Yes, okay. Gotcha. X not fixed. X is fixed, sorry. Okay, that solves that problem. So yes, the expected value of the thing is just going to be the thing. What about the expected value of... so a plus e squared is blah blah blah, where a is equal to f minus f hat. or x not fixed. No more subscripts. Yeah, so what I have left over, zone, is the 2ae plus e squared thing. Is that So now I'm just wondering how I get this variance piece out. So I understand this. This makes sense to me. So I'm cool with that. That's great. How do they, like, how is this expected value where x is fixed connected to this? I guess that's what I'm trying to think about next. Right, the expected value of these errors is 0. Yeah. Okay. So the expected value of the errors themselves is 0. So can we rewrite this as 2? We know f of x is fixed, so 2f of x expected epsilon minus 2 f hat x expected value of epsilon plus expected value of epsilon squared. We know that these are going to be 0 because e of epsilon is equal to 0. And then the expected value of the squares is the variance. Yep, that's all I needed to. I needed to remind myself some of the things. There were some assumptions here, and I was just like, I just couldn't put all the assumptions together. Cool, okay. Yes, so now I agree with exactly everything they said. Yeah, it was not that hard to show, but me not knowing the assumptions didn't make it easier. Okay, cool. I'm cool with that. That makes a lot of sense. Unfortunately, I think with that, I do actually have to run to the college, so I am going to be ending here. So I'm going to be posting up some news in the ML Announce 2025 and the elements for a schedule for this week. I'll probably try to keep this discussion going. So I liked what we did today, right? I like that we had like a little bit of a discussion. There was a little bit of math today. I want to keep on reading through chapter 2 of the James textbook so that we can get a more of a statistical introduction to machine learning. And then our goal is to maybe skim through chapter 2 of Reese during the week. And then next week on Friday, we'll start chapter 3, which is classification. And I should have a bit more time. I won't have to run to a meeting hopefully next week, so we can actually do some coding, do a little bit more of the statistics stuff. So which textbooks? I know all the sneaky assumptions, Obi. We were on page 19 of the James textbook.
Time's not on your side, just like math. It marches forward. Keep your equations in check. You'll need them to survive.
So we read chapter 1 of Reese, and we got up to page 19 of the James textbook. Yeah. And I'm going to try to keep on kind of reading through chapter 2 of the James textbook during the week and just kind of have discussion in Discord if there's something that I can't figure out. But yeah, I'll try to post all that up when I get back from my meeting. Is anybody online right now? I only have Tinker on right now on my monitoring computer, but that tends to not always have everyone that I need to have on. No, it's pretty quiet today, eh? Fridays are quiet for math. Alright, I guess we end here, folks. Many people are online. Yes, it's true. No one doing math, though. Alright, we're going to end here, folks. Thanks for the stream. I will catch up with you at some point over the weekend. Bye, everybody.